In this video, we're going to talk about Part C of Example 6.2 in the OpenStax textbook, which you can download for free using this link. Okay, so in particular, what this example is talking about is using z-values to compare two different random variables. Okay, and so we already talked about Part A, Part B, so now we're moving on to Part C. Suppose the random variable x and y have the following normal distributions. Okay, so I'm just going to write it down here. X is normally distributed with 5 and 6, and y is normally distributed with 2 and 1. Okay, so remember, the first number is always the mean, the second number is the standard deviation. So y has a different mean, mu, and a different standard deviation. Okay, so if I were to draw all these distributions, here's x, the distribution of x, centered on 5, right? Versus the distribution of y, so it's slightly narrower because the standard deviation is 1, but still normal, bell curve, and it's centered on 2. Okay, so if x equals 17, so little x is 17, then z equals 2. All right, and they're saying that that was previously shown. They're saying it was previously shown. Really quick, I'll just show it really quick. Z equals x minus mu over sigma, right? So if x is 17 minus mu for x is 5, sigma is 6. So that's 12 over 6, which is 2. Great. So we got it too. We got it as well. Z equals 2. Okay, so if y equals 4, what is z? So little y equals 4. Okay, what is z? So again, we'll use the same formula. Now instead of starting with x, we'll just have the random variable y. But it'd be y minus mu divided by sigma. Same thing, except it's just a little y there instead of an x. All right, and we write 4 minus mu, which is 2, and sigma, which is 1. Right? So remember, I'm looking up here for this mu and this sigma. Okay? So 4 minus 2 is 2 divided by 1, which is 2. Very interesting. So what is z? Z is also 2. All right? So they both have the same standard deviations away from the mean. Right? So going back over to the x, little x was 17. Right, so that's way up here, 17, right? And that's 2 standard deviations above the mean, okay? And then looking over to the y, little y is 4, right? 4 is up here. And that is, once again, 2 standard deviations above the mean, right? Because z equals 2 in both cases. So both 17 and 4 are both 2 standard deviations above their means, okay? Okay, so the book gives this nice little paragraph to summarize what I just said, but basically this z-score allows us to compare data that scale differently. So say x, which remember was normally distributed with mean 5 and 6, right? 5 and 6, and then y, which is normally distributed with mean 2 and 1, right? It's slightly more narrow, okay? And then we had our observations at 17 and at 4, okay? And they both were 2 standard deviations above their mean, right? For both of them, z equals 2 standard deviations, so z equals 2, right? So both 17 and 4, they're both 2 standard deviations above the mean. So if x was the weight gain for one group and y was the weight gain for another group, so then someone who gained 17 pounds gained the same amount of weight as someone who gained 4 pounds relative to their groups, relative to their means. So since x equals 17 and y equals 4 are both 2 standard deviations above their means, they represent the same weight gain relative to their means.